Hi, I'm Emily Karen Krause.
I'm Peter Hollander.
I'm Benjamin Kitchen.
I'm Emily Lopez.
And I'm Ashley Zwang.
And we are the Graph Theory and Throttling group in the Small 2020 RU this summer. And we've been working on throttling for zero forcing on directed graphs. So we're going to start with just definitions of zero forcing and throttling, and then we have two main categories of our results that we're going to talk about: first characterization theorems, and then orientation throttling intervals, and then we'll talk about some things we're going to do in the future. So while a graph is defined by a set of vertices and a set of edges, where each edge is an unordered pair of vertices, a digraph or directed graph is defined by a set of vertices and then a set of arcs, where each arc is an ordered pair of vertices, so implying a direction along each arc. And a digraph can have loops, parallel arcs, and doubly directed arcs. And then a simple digraph is a digraph, but it can't have parallel arcs or loops. And then an oriented graph is just a simple digraph, but with no doubly directed arcs either. So here we have an example of a digraph. So the two higher arcs are parallel arcs since they're going in the same direction and starting and ending at the same vertices. And then we have a doubly directed arc below that. And then at the bottom, there's a loop. And then we can turn it into a simple digraph by deleting one of the parallel arcs and the loop. And then we can turn it into an oriented graph by picking a direction for that doubly directed arc. Also, if gamma is a digraph with vertices u and v, an arc going from u to v, then v is an out neighbor of u and u is an in neighbor of v.
Our research project this summer relies on a coloring game on a digraph called the zero forcing process. And this is where we are given an initial coloring of the vertices as either blue or white, and we repeatedly apply the following color changing rule. That is, if a blue vertex u has exactly one white out neighbor v, then u will force v to turn blue. And if a subset of blue vertices of a directed graph can color the whole graph blue after repeatedly applying the color changing rule, we call this subset of vertices a zero forcing set. So given a zero forcing set of a digraph gamma and initial coloring of its vertices, we are able to apply the color changing rule until it is no longer possible. And the set of forces used in this process we call a set of forces of a zero forcing set. We denote this as F. And to gain a better understanding of how the coloring of the digraph is changing as we apply these forces, we adopt this notion of a time step of a set of forces, which we define as follows. We let F0 to be the zero forcing set, and after t iterations of applying the color changing rule, we have a coloring of the graph where there are a subset of vertices colored blue and the others colored white. With this coloring, we perform all forces that can be done simultaneously, and we call this set of vertices that are just recently forced ft plus 1. This enables us to now talk about the propagation time of a set of forces, which is the smallest amount of time steps needed to be able to color the whole graph blue using a set of forces. However, this is different from the propagation time of a zero forcing set. The propagation of a zero forcing set is the minimum propagation time over all set of forces for a zero forcing set. And this is usually achieved when we perform the maximum number of forces at each time step. So to give an example of this, we look at this path on 5 vertices, and the 2 endpoints are in the zero forcing set. Now, because each of these vertices that are colored blue have one unique white out neighbor, they're able to force these vertices at time step 1, which is indicated by the number above these newly colored vertices. Now, these vertices are able to color the central vertex blue because they only have one unique white out neighbor. Therefore, the propagation time of the zero forcing set is 2. Our research project mainly focuses on the throttling number of simple digraphs gamma, which we denote as th of gamma. The throttling number is the minimum value of the sum of the cardinality of the zero forcing set and the propagation time of the zero forcing set, where we are considering all zero forcing sets for a digraph gamma. So to better illustrate this concept, using the previous example of the path on 5 vertices, a totally valid zero forcing set is coloring all the vertices blue and propagating in 0 time steps. This makes the sum of the the cardinality of the zero forcing set and the propagation time of the zero forcing set to be 5. However, this zero forcing set does not achieve the throttling number, as we saw in the previous walkthrough example of the zero forcing set on 2 vertices, and that was able to propagate in a total of 2 time steps, thus making the sum of the cardinality of the zero forcing set and the propagation time of the zero forcing set to be 4, which just so happens to be the minimum sum.
Now we're going to work towards a characterization theorem for digraphs with respect to their throttling number. But to do that, we're going to first need to cover a couple definitions. So first, referring to simple graphs, when we say we delete an edge, we basically just take the resulting graph minus a given edge from that edge set. And when we say we contract an edge, we, as you see in this diagram below, we basically take either endpoint of an edge and merge them into a single vertex and delete any parallel loops or arcs. We're also going to use a few simple graphs. We're going to use a complete graph, which is a graph where between any 2 vertices, there is an edge between them. And we're also going to use a path, which is basically a sequence of alternating vertices and edges. We're going to use these 2 graphs to talk about this Cartesian product of Ka and Pb plus 1, a complete graph and a path. And we're going to refer to the complete edges as the edges within each column. Those are the ones with the dotted lines vertically. And the path edges are the edges within each row. We're also going to refer to a digraph called HAB plus 1, which is basically a graph where you arrange A by B plus 1 many vertices in a lattice with those dimensions, make each row a directed path going to the right, make each column a doubly directed complete graph, and then make all other possible arcs oriented going to the left. So we're going to construct an example of this going step by step. First, using a 3 by 3 lattice, we're going to make each row a directed path going to the right, and then we add complete arcs within every column. And then lastly, we're going to add a bunch of backwards arcs wherever we have not yet created an arc. And so when we combine these 3 steps, we create that graph HAB plus 1. It's important to note that the arcs that we constructed in the first step, the path arcs, the arcs going to the right, are the only ones we will refer to as path arcs, and all other arcs we will refer to as non-path arcs. And once again, in digraphs, edge contraction just goes the exact same way. It is the result of taking either endpoint of an arc, merging them into a single vertex, and then deleting any loops or parallel arcs. So this is an existing theorem, characterization theorem for simple graphs, and it simply says that given a simple graph G and a positive integer t, the throttling number of G is less than or equal to t if and only if we can find integers a greater than or equal to 1 and b greater than or equal to 0 that sum to t, and we can obtain G from this Cartesian product graph by contracting path edges and deleting complete edges. And we found that there's actually an analogous theorem for digraphs, namely that the throttling number of a digraph is less than or equal to t if and only if, once again, we can find these integers a and b that sum to t, but now we can obtain the digraph from this HAB plus 1 host graph by contracting path arcs and deleting non-path arcs.
So now we're going to talk about all the different throttling numbers that are associated with a simple undirected graph. So first we need to define an orientation of a simple undirected graph G, which we'll denote as G with an arrow on top of it. And this is an oriented graph such that ignoring the directions of the arcs gives the graph G. So we're pretty much just adding a single direction to each of the edges in G. And the orientation throttling interval of G, or OTI, is given by the closed interval between the minimum possible and the maximum possible throttling number achieved by any orientation of G. And we say that this OTI is full if for every integer within this closed interval, there is some orientation of G that achieves that number as the throttling number. And we're actually going to prove now that the orientation throttling interval of every graph is actually full. So to do so, we need one last definition, and that's this process we call flipping an arc, which is exactly what it sounds like. It's just replacing an arc AB in a digraph with the arc BA. So simply just switching the direction that it goes in. And now we're going to prove this lemma that if you have a simple digraph, when you flip a single arc, given that it's not part of a doubly directed edge, then we know that the throttling number will not change by more than 1. And we'll first start by proving this, proving that the throttling number will not increase by more than 1. So we start with any simple digraph and a set of vertices that achieves the throttling number. So this one is just for illustrative purposes. This graph happens to have a throttling number of 6, which can be achieved by coloring these left 2 vertices and propagating it in 4 time steps. And we see that conveniently we've drawn this so that the forcing arcs, the arcs that forcing happens along, are the horizontal arcs. So now, in the first case of this proof, we're going to consider flipping an arc that is a forcing arc. So we're going to flip this one that's now dashed and label those endpoints A, B. And what we're going to do is we're going to add B to the initial forcing set. So now our initial forcing set has 3 vertices in it. And we see that even though we flipped a forcing arc, so now A cannot force B anymore, that doesn't matter because B is already blue to begin with since we've added it to the initial forcing set. And also B is the only vertex that has gained an outneighbor, namely A, but A will already be blue by the time step that B had originally forced because A had originally been the vertex that forced B. So therefore, B's forcing will not be stalled at all, and propagation time will not increase in this case. Now in our second case, we're going to flip a non-forcing arc, which is this diagonal dashed arrow, and we also label the endpoints A, B, and this time we're going to add A to the initial forcing set. And we see now that B is the only vertex that gain an outneighbor again, namely A, but A starts blue in the first place, so A will not actually stall the forcing for B. And since all the forcing arcs remain intact, we can just use the same set of forces, and since propagation won't be stalled, propagation time does not increase. And since in both of these cases, we added 1 to the initial forcing set, and the propagation time does not increase, that means that the throttling number will not increase by more than 1. And since the throttling number can't increase by more than 1 when we flip an arc, it also can't decrease by more than 1, because if it did so, then you could just flip that same arc again, and it would be increasing by more than 1, and hence we would have a contradiction. So now from this lemma, it immediately follows that the orientation throttling interval of any simple graph is full, because we can just start with the orientation that achieves the minimum throttling number, flip whatever series of arcs we have to attain the maximum throttling number. And by this previous result, every throttling number between the minimum and maximum has to be achieved by one of these intermediate graphs, because it can only change by at most 1 in each flip.
So, with this concept of an orientation throttling interval, you might be wondering, are there bounds? Can throttling not get lower than certain values? Can it not get higher than certain values? And the answer is yes. In particular, the lower bound for throttling, regardless of orientation of the graph, is the ceiling of 2 root n minus 1, where n is the number of vertices in the graph, and the upper bound is just n, the number of vertices in the graph. The reason for this lower bound is that we can find the same lower bound when we're throttling an undirected graph. Finding this lower bound relies on some calculus that derives from the fact that every vertex can only ever perform a force once. This restriction still exists when it comes to throttling on an oriented graph, which means we can use the exact same calculus and get the same lower bound. Now, the upper bound of n comes from the fact that we can just fill all the vertices from the start and force everything in n. And force everything in 0 time steps, yielding a throttling number of n. Because we can always achieve this, it follows that because throttling number is a minimum, we can always achieve this, so we can't do any worse than this. All right, now a tournament is an orientation of a complete graph, which Peter introduced a few minutes ago. These are interesting because the orientation throttling interval of a complete graph is in fact maximum. That means there's an orientation that achieves that lower bound and an orientation that achieves that upper bound. So first, we're going to construct a tournament that achieves the upper bound of n. And to do that, start with a vertex A, add a vertex B, such that A is an outneighbor of B. We repeat this process, add a vertex C, such that B and A are both outneighbors of C, and repeat until you have as many vertices as you would like. If 2 vertices can perform a force at the same time in this orientation, you can convince yourself that those 2 vertices would have to be forcing the same unfilled vertex by how this graph was constructed. Therefore, during every time step, a maximum of 1 force can occur, so it follows that the throttling number has to be n, and we cannot throttle this graph any faster. As for the minimum, do the following. We have number of vertices n. Pick a number, for specifically the largest perfect square less than n. We'll call that m squared. Take m squared vertices of the n that we have and arrange them in an m by m lattice. If n minus m squared is greater than 0, take the remaining vertices and put them in the rows above this m by m lattice. This example down here is for when n equals 5. The largest perfect square less than 5 is 4. We get a 2 by 2 array, and then the extra vertex just goes on top. 2, orient this so it achieves the lower bound. The columns, it genuinely doesn't matter. We don't care. Do whatever you want. The horizontal vertices in the rows have to go from left to right, or horizontal arcs, excuse me, have to go from left to right. All other arcs, which are the diagonal dashed ones depicted here in this example, go from right to left. Now, if we fill the leftmost column, this will propagate in 1 time step in this particular graph, or for this particular value of n. It is true, there's some algebra that we have excluded for the sake of time, that if we do this process with any number of vertices n, we will always get that this throttles in ceiling of 2 root n minus 1. Or we achieve a throttling number of ceiling 2 root n minus 1, which means this achieves the lower bound. Now, you might be wondering, we have this upper bound, we have this lower bound, we have a graph that achieves both bounds. Are there graphs that achieve neither bound? And the answer is yes. We're going to construct a family of graphs that achieves this like so. Let G be a double star on n minus 1 vertices. A double star is the type of graph depicted below. That's just an example. 2 vertices in a double star have degree that is not 1. Specifically, it's greater than 1. Pick those vertices and call them A and B. By how double stars are constructed, there's an edge connecting A to B. Take that edge out. Replace it with a vertex W, then connect A to W and W to B. We now have a graph on n vertices that we're going to call an augmented double star. And it is the case that for augmented stars on 12 or more vertices, it is impossible to achieve the lower bound, and it's impossible to achieve the upper bound. Once again, the proof of this has been omitted for the sake of time, but this is a true statement.
So these have been all of our main results, but things we're still working on is wondering if for any given simple undirected graph, can you orient it to achieve the same throttling number on the orientation as the original graph? We're also still working on proving what the orientation throttling interval of a path is. Turns out when you orient it, it gets really complicated. And then also we're kind of investigating whether maximizing the number of vertices with only out neighbors or only in neighbors maximizes the throttling number, because it seems to. And then also looking at other graph operations and seeing how they influence throttling. But yep, that's what we're doing in the future. Thanks for listening.